today. Hopefully when I get home. All right, let's look at this. So section 1.4 is what we're going to look at. All right. So for 1.4, I'm going to kind of divide into two parts. One part we're going to talk about functions in general. Like I usually just talk to my students about having a toolbox of functions. We'll do that. I'm going to let you use Desmos on that for a little bit. Then, we'll get you in and out of here too when we're doing that part. Then we're going to come back and look at what we call piecewise functions, those step functions, and we'll do a couple problems, and we have our first quiz, and then we're done. So that's kind of our schedule for today. So let's look at, again, this is section 1.4. It's in the two parts. Okay, so let's just take a look at our little toolbox here of functions. Okay. So what we're aiming for is being able to look at a graph and say, what is that? All right, what makes that graph? So for instance, the very most simplest we would have is a linear y equals mx. Okay, not even a b associated with it, just y equals mx or y equals x even. Okay, that would be a linear function. All right. So what we want to do is, and I'm going to write the functions down for you. They are in your book, but I'm going to write them down for you. We're interested in what the domain is, what the range is, okay? And then we're going to make a little graph of what it looks like. Okay? So, for instance, y equals x, I know what that is, you know what it is. We've got a line here. Okay? And the domain of that, for all lines, okay, what's our domain going to be for all those lines? All reals. All right, good. All reals. Doesn't matter what we do to that line, it's always all reals. What about the range? All reals. Okay? We could restrict it, I guess, and chop it off, but most likely that's going to be, domain and range going to be all reals. All right? So, the next ones that we're going to take a look at in here are what we call power functions. Okay, and here's where I'm going to have you do some exploring here. All right, so y equals x to the n, where n is even. We need a domain and a range. Y equals x to the n, where n is odd. We need a domain and a range. All right? So I'm going to have you explore those. And I'll do them all. I'm just going to write them all down, and then I'll try to make it so you can still see them if you're not getting all this written down. All right? So those are that. Then we have what we call, well, powers contain a lot of different things. Inside the powers, we have these. So like that's a square root. So we have an n here and an n here then. So again, we have an n is even, domain and range, and n is odd, domain and range. Okay, and we also want to make little sketches of their graphs. Okay, they don't have to be great sketches, they just have to be little ones so we can kind of associate the basic shape of the graph to the function that it is. All right, so we have that. We have this one. Okay, domain, range, graph. Absolute value, we have roots. Absolute value is not a power function. Okay, we have this one. All right, domain, range, make a graph of it. That's a rational. And I have one more, or a couple more I want you to look at. In Desmos, you're going to find one that's floor, and ceiling. I want you to look at those, okay? So, here's the ones we're looking at. I'm trying to make it smaller for you here. Almost so you can't even hardly read it. So what we're going to do is take each of these, or what you're going to do, and type them into Desmos. You can make sliders if you want to. All right. If you type y equals x to the n, and it's going to ask you to add a slider, and you can slide in and investigate it that way, or you can just type some even ones in and type some odd ones in. Look at the domain and ranges, make a sketch of the graph. Do the same thing for the roots. Okay. Desmos has, if you go to miscellaneous, it will have a root, and it will have your ability to put in any power that you want. Okay, it's under MIS. Check it out. If you're not sure where to find it, ask me. Absolute value, it's there. Just got to look for it on the little keyboard thing. 1 over x is self-explanatory. Floor and ceiling, are in the miscellaneous. All right? So, here's what we can do. I want you to explore these, but it's obviously if you need to take a break, get outside, or for a little bit, you can. All right? All right. I'm assuming that you've had a chance to look at these. Okay, power function, n is even. What's our domain? Somebody give me an answer.
All real.
All real. Excellent. Range.
0 and positive infinity.
Okay. And let's see, let me get a graph here. And to best describe the graph, what do we got?
Very skinny U.
U's. Good, I like it. All right. So whenever we see a U graph, we should associate that with an even power function. All right, that's where we're heading. Okay, sweet, let's keep going. What if it's odd? Domain? Range? Graph?
Curves up and curves down from 0.
Okay. Something like that. Right? Okay. Sweet. Okay. An even root. Domain? Okay, 0 positive infinity. Good. Range? Same thing. Okay, so tell me about how I would do the graph of this.
Curving up to the right.
From 0, curving up and to the right. Very good. Good. So we have power functions that are evens and odds. We're getting those types of graphs. This is still a power function. Okay. It's just that it is a root, which means that this with x to the n would have to be a fraction. Okay. So these are fractional. So if we wrote it as y equals x to the n, where n was a fraction, we're going to get a root. All right, let's do the odd part here. So let's see. Odd ends. Domain? 0 to infinity?
I put all real numbers.
You put all real numbers, okay? So we have a little bit of a difference of opinion here. So what do we got? What are we thinking? Anybody else got some ideas? Let's graph it. Okay. I'll graph it. Y equals functions. Here we go. Give me an odd number then.
3.
All reals. There we go. Okay. All reals. Great. Range? All reals. Okay. And we saw the graph, so let's see, we've got something like this, and then something like that. Okay. Absolute value. Domain? All reals. Range?
0 to positive infinity.
Graph.
B from 0.
Very good. So anytime we see a V graph, we might think absolute value. All right. Okay. Let's see what happens here. We've got y equals 1 over x. Domain? Negative infinity to 0. Is that a bracket with the 0 or a parenthesis? Parenthesis. Okay. And then what else do we have? Okay, so you're saying union. All right. And that's very, very formal. To what? Positive infinity. Okay. Or we could just say this too, right? Okay. So I don't care which way you use what you use, all right, as long as you're telling me the correct answer. All right. Yeah, you can put a U in there if you want. I know what you mean if you tell me that. Okay. You can put a U in there if you want. You know, you probably had some math teacher that drilled you and said that's what you got to do. Just 2 weeks ago. Okay, I'm not saying that's wrong. I'm just saying we don't. That's okay. All right, range. Okay, same thing. All right. All right. Oh, I didn't graph that. Here we go. Okay, what do we got? What does this look like? Hard to describe. Okay.
Left on the negative x, it's going from infinity and curving down.
Okay.
Reciprocal.
Okay. So this is one of those. Remember, we had those ones that were odd evens, right? We did that rotation. Okay. That's definitely has that symmetry. Okay. So that rotation. Good. Hey, we got a couple more here. Let's see what we got. Domain for floor. All reals, it's not? I got a couple heads bobbing this way. So what do we think? All reals or not all reals? And if it's not all reals, what is it? Did you find it?
I graphed it, but I mean, it was similar to the graph we were drawing with the X question that you showed earlier. So it'd just be whole numbers, wouldn't it?
For the domain? I agree with you. It was similar to it.
All real.
All real? So let's take a look here. So if we go y equals functions, miscellaneous, floor, x. Change, here, let me do this so we can get a better, I should have that on all along. There we go. So what do we think? All real?
Sure.
Sure.
Let's go for it.
So if we go along here, every number is represented, right? If we push this up here, push this down here, it's going to cover everything on that x-axis. And it passes vertical line test, yep. Okay? So, all reals. Ah, but the range. Thing to show back up. So the range, we're looking at the y's. So if I just kind of go through this, jump, I'm looking at the y's. So you're right about those are definitely the whole numbers there. So what are we thinking?
I don't know how you would format that. Like, how would you represent that? Besides just saying like writing all whole numbers.
But I don't know if it is all whole numbers because do you remember what a whole number is?
1, 2, 3.
1, 2, 3, right? 0, 1, 2, 3.
Yeah.
So how are you going to count for these ones down here?
All integers.
All integers.
Okay.
Okay? All integers. So then what we want to put down is all integers. Okay? Oops. Like right in the wrong spot. Now, before I draw the graph, I'm going to come back and do ceiling here. What about the domain for ceiling? All real?
Yeah.
Okay. What about the range?
Also all integers.
All integers. Okay. What does floor and ceiling do? What are they doing to the domain? What's our output and our input? What's happening?
Rounding up and rounding down.
Good. Rounding up and rounding down. Which one's rounding up?
Ceiling.
Ceiling. Because that's up. Which one's rounding down? Floor. Okay. So what do we mean by that? So if we take, right, if I say, hey, I want to know what the floor is of 3.4, what is that going to spit out to me? Because it's rounding downward, okay? Ceiling, if I want the ceiling of 4.8, what is that going to give me? 5, because it does what? Okay. What about the ceiling of 2.1? What's that going to give me? 3, because what's it going to do? Round up. What about negative 2.4?
2 or negative 2.
Going to go to negative 2, right? Because what's it doing? Rounding up. Okay. So we kind of have to watch that. So floor and ceiling, that's what those do. All right. So if we go up here and try to look at this graph, all right, and I try to draw it here, I guess I've been using this color. 0 is 0, but then once I get to point 1, what is floor going to, or excuse me, which would I write here first? Floor. What is floor going to do to point 1? Where is that going to give us? It's going to be 0, right? So it's going to be 0, 0, and I'm going to hit a number 1, okay? And then what's the floor of number 1 going to be? 1. So it's going to bounce back up. Okay, and I don't remember in the back was talking about, or I think, about the open circles and the solid circles, right? That's where that's going to happen. Okay, so we're going to have this kind of a look, right? So it keeps it a function because of the vertical line test, and we don't have an x value relating to two y's, right? And the same thing's going to happen here. So that's what floor does. Ceiling, 0, but what's going to happen as soon as I hit point 1? It's going to go to 1, right? So then I got this kind of a look. And then right at 1, then I go to 1.1, and then all of a sudden it goes to 2. Okay? So then we get this type of a graph here. All right? That's our steps. You might have noticed that there's another one in there called round. Okay? And round, did anybody try round by any chance?
Either less than like 0.4 or lower, then it goes down, 0.5 or higher, it goes up.
That's right. It's just our normal rounding. Okay? It's just our normal rounding. All right. So that's a couple different things in Desmos on floor and ceiling. In the textbook, okay, they talk about the greatest integer function, okay? And the greatest integer function is very similar to floor.
What page?
82. So greatest integer function. Okay. So you can see that what it does is as soon as it hits between 0 and 1, it's 0, but then as soon as it hits 1, it bounces it up. So it's rounding it down just like floor does. Okay. The greatest integer is sometimes notated by this. Okay. I've also seen it as INT. Okay. So it can be written in a number of different ways, but that's the greatest integer function. It's just like floor. So the greatest integer of 1.8 is just going to be 1. It's going to round that down. All right. Or INT. I think that's what our book uses. Okay. There's a little paragraph in there about a discontinuous versus a continuous function. Okay? So a continuous function, basically, if you can take your pen or pencil, right, and you can trace the graph of the function, without lifting it, it's continuous. All right, so if I can trace the graph of the function without lifting your pen, pencil, whatever you have, the function is continuous. Okay, so most of the functions that you have done up to this point are all continuous. Those lines, the parabolas, the roots, all those were continuous. As soon as we have to do something with steps, discontinuous. As soon as I have to do something with these rationals, okay, discontinuous. Because I'm lifting up my pen or pencil. Okay, to trace them. So I trace it, lift, lift, lift. Okay, sketch, lift, do that. Right? So it's not continuous. Okay. Hey, any questions on any of that stuff that we did there?
Would a piecewise defined function also be odd?
They could be, but we haven't done those yet. That's our next thing. But we could be. You mean as far as being symmetric? Yeah, you could make one that is. Mm-hmm. Okay. Uh-oh.
Did you look at the storm?
Oh, you were pretty excited for a minute there, weren't you? You're going, hey, we're leaving. Okay. I'm gonna have to wait here. We do get a pause. Oh, everything. So we'll do piecewise here. I'm going to pause. All right. So let's take a look at some piecewise functions here. So a piecewise function is kind of the way it sounds. It's built into pieces. So, for example, you have a function and a condition. So I'm just going to say something like this. Oops. All right. So this is built into pieces. Okay, so here, this function happens under this conditional. This happens when x is equal to 0, and this happens when x is greater than or equal to 0. So it's built into pieces. All right, and it always has some sort of a condition. Okay, so this is the condition here, and the function here. So what does this look like? Well, we're going to do some by hand, and I'm going to show you how to graph them in Desmos. So let's say that x is less than 0. Okay, so let's say we have all these things over here. All right. So when x is less than 0, what kind of a function is that? We should know that now. 2x is a what? Linear, okay? It's linear. All right. So, for example, then, if I have negative 1, I know I'm going to have a negative 2 here. So I have negative 1, I'm going to have a negative 2. And at negative 2, I'm going to have a negative, what happened to my, here we go. At negative 2, I'm going to have a negative 4, and so forth. So I'm just going to have this line, okay, like this. All right, until I hit 0. All right, what's happening at 0? So what are we getting at 0? 3. Okay, so I have an open dot there, and now I have a 3. Okay, what's happening when x is greater than 0? Then what's the condition says I do what? 2x squared. So then I'm going to go 1 squared is 1 times 2 is 2. So it's going to look like that. 2 squared is going to be 4, so that's going to be 8. So it's going to be way up here. So I'm going to get this sort of parabolic looking thing. So it's going to look kind of like this. Okay, so I have this with an open dot, 3, and then here. All right? So that's what that looks like. It's a piecewise function. Is it continuous? No, because we have to lift our pencil, do that, and then come back down. Okay, some piecewise functions are continuous, some are not. All right? So how do you do it in Desmos? I'll show you. Yeah, it says the projector is warming up on my thing here, but we'll get into Desmos here as soon as I'm able to. And I'll show you how to put them in. Basically, all you're going to have to do is just graph them and look at them a little bit. You're not going to have to do a whole lot with them. They want you to find the domain, locate intercepts, graph them, find the range, say if it's continuous. Hope this didn't mess everything up here. Okay, sorry, let's turn this whole thing off. So we'll go into Desmos, all right? What we're going to do is in Desmos, however, it flips the condition and the function. Okay, so you have to do the condition first. It's just the opposite. I'm not exactly sure why they designed it that way, but maybe there's some programming reason for it or something. But they flip it, okay? So when you go in there, I'm going to go y equals, and we need that curly Q bracket. Okay, so the curly Q bracket, I can get that by doing the ABC and hitting here. All right. All right, I'm going to put a y equals in front, but I'm kind of jumping here. I don't have to, but I like to. Okay, so here I am. So now what I'm going to do is put the condition in first. So for the one that I did, I would go x less than 0. Okay. Now, after I put that in, I need a colon. Okay, and the colon in mathematics means such that. So to do that, I go down here to ABC. There's my colon, but I have to hit the shift to get that. And I know you can just enter it on your keyboard, but if you're using your phone or something different, and you have to do it this way, all right, that's why I'm showing it. Obviously, you can use your keyboard. All right, then you're going to put the function in, all right? So that would just be 2x, okay? All right. Then we're going to go comma. So the comma is separating the lines of the function. So our first one was 2x, x is less than 0. Now I'm ready to put in the middle one. All right, so that would be just, I need to put in my condition first. X equals 0 such that, all right, now I put in 3, okay, comma, because now I'm entering the last and final line. I got to put the condition in first, x greater than 0, such that (2x squared). And there it is. All right. Yeah. So if we trace along this ever so slightly, you'll notice it should jump up there. As soon as I hit 0, that's, okay, it does jump up there. It did once. I know I didn't do it again. There it goes. Okay. So that's how you enter in a piecewise function. All right. It's just you got to get the syntax correct. If you don't put the commas in the right, the colons, it messes it kind of up. All right, and that's really all you have to do. All right, is just kind of put them in and list the domain, intercepts, graphing it. You can just sketch it, find the range, and if it's continuous or not. Okay, pretty straightforward. So let me do this here. I want to go to this. So let's look at something along the lines of an application maybe of a piecewise function. So by the way, income taxes are a very good example of that, but I had came up, and parking too. But here's something, let's say we're mailing a package, or we have a company that mails packages, and to a certain city, if it's 0 to 1 pound, we have a flat rate of $2.25, all right? If it's 1 to 5 pounds, it's $2.40 a pound, and if it's 5 pounds to whatever, so it's just greater than 5, it's $3 a pound, okay, plus a $10 flat fee for having such a heavier package. All right, so take a couple minutes, see if you can write a piecewise function that matches that. So it's $2.25 flat rate for 0 to 1, okay, not including not including one, sorry, so that would be including. And then from 1 to 5, $2.40 a pound, and then 5, $3 plus that fee. So it does include this number, so I'll just put like a little box around it so you know that it includes that number. Okay. See if you can write a piecewise for that. What do we got?
2.25x as the function.
2.25, sorry. X?
Yes. And that's 0, less than or equal to x, x greater to or equal to 1.
Okay, agree with that? We all agree with it? No. What should change?
It's a flat rate, so it's just going to be 2.25.
Okay, so it's a flat rate, so we just want 2.25. Okay, good. Okay, it's okay. In case I want answers, so just don't worry about if they're not quite there. You're close. That's all that matters. All right. Next, what do we got? Keep it going. 2.40 x. And what am I going to put there for the condition? So 1, so we have x is greater than 1, but 5. Okay, good. And then what do we have after that? 3x plus 10. And my condition?
X is greater than 5.
Okay. All right, let's take a look at it here. Get rid of this guy, put this in down here. Y equals so now remember Desmos, you got to put that condition first. All right. What are we going to put between them? Awesome. And then what do we put to separate the functions? Comma, very good. All right, good, good, good. And then I have a colon. I need 2.4 x, sweet. One last one, x greater than 5. Such that, and then I put the function in, x plus 10. Okay, so there it is, all right? Okay. Again, it's a function because even though it doesn't show, all right here at 4.9 is 11.6, and getting closer and getting closer. 5 is 12, and then as soon as that's as far as I can go. Up here, it gets real close to 5, but see how it bounces back down. Okay, right at 5. So that clears it, makes it a function. Continuous? No. Okay. Domain?
Zero to infinity.
0 to infinity. Good. Range?
We got like 2 to 12. And then
Oh, that's right. So we start here at about 2 1/4, right?
yeah.
We get to 12, and then there's nothing. So then it picks up again at
25.
25.
Yeah.
Okay. So there's a spot in there where the range doesn't exist. All right. Good. We picked up on that. Sweet. Awesome. Okay. So here's what I want to do then. I just want to do just a couple of these problems here, and we'll take our quiz, and then we will be done